we're going to do this in English. If there's anyone online who wants to ask questions, just unmute yourself and go ahead. How much time do we have for this? 45 minutes. Okay, good. So we're definitely going to be running out of time, but we'll see how this goes. Okay, so today, as the title suggests, we're going to be talking about disentangling multi-qubit states using reinforcement learning. And this is actually research which is made here in Bulgaria by Stefan and Pavel, who did their masters at the Faculty of Mathematics and Informatics. They graduated from the AI program there, and in particular, Pavel's master thesis is pretty much related to this. But this was also done in collaboration with Friedrich Metz from EPFL in Lausanne. So I'd like to start by if I can move anything, maybe I start. Let's see how that goes. Okay, now it goes. Good. So let's get started. So as the title suggests, today's talk is going to be about disentangling multi-qubit states. And I'm just going to start with a simple picture here. So what you have here on the left is a couple of qubits, and these qubits are in some state that is entangled, and the entanglement is shown by these dashed lines here. And so you can think of these qubits as qubits that are part of the quantum computer, if you wish. And what we want to do is we want to apply 2 qubit gates, a sequence of 2 qubit gates, in such a way that at the end of the sequence, the initial entangled state is brought to the product state of all zeros. Now I'm not sharing anymore. Then I have to start sharing. Yeah, but now I can't really. So I think it doesn't let me. Okay, now it's okay? Yeah, good. All right, so for those of you online, we start with an initial state that might be entangled, and we're looking for a sequence of 2 qubit gates in order to disentangle it, that is to say, to bring it into the product state. And of course, as the other part of the title suggests, what we want is we want to do this using reinforcement learning. And of course, I don't expect that any of you knows how that works. So the whole point of the talk today will be to explain to you how to disentangle states and how to do this in particular using reinforcement learning. So that's going to be the idea for today. And before we start, what I want to do is I want to show you a movie of how our reinforcement learning agent actually works and how it disentangles states live in time. And this is a movie that Stefan prepared in the last week or so. So let me first explain what you're going to be seeing here. So you see basically four graphs more or less. On the left, you see the circuit. So these are the initial qubits. We're going to initialize them in some random state. That's the whole point of using machine learning. So you give me any state, and then my agent is going to disentangle it. And then what you see here are those gates shown in black. And you kind of see the dots are indicating which qubits the gate is applied to. And in between, we have these blue circles, and the blue circles are telling us the amount of the entanglement between this qubit and everything else. And it doesn't really matter how much the entanglement is for the purpose of this movie. What you should look for is the color here, because the color can change from blue to green. And as it does so, the entanglement goes down. What you can also do, of course, is you can look at the entanglement as a function of the time, as a function of the gates. And this is shown here on the log scale. So this block shares the same axis, the same time step axis. And the whole point now is to show you a movie how the agent learns, starting from no knowledge whatsoever, to disentangle arbitrary states. And the way the agent is going to be disentangling the state is the agent will be choosing those gates, okay? So it will choose the gates according to a strategy, which is probabilistic. So the strategy is shown here in the lower right corner. The idea is that there will be like probabilities, and then every gate will be taken with a certain probability. And the last plot before I run this is this here. So this is the optimization curve, if you wish, how well the agent does as a function of the training iteration. And then the higher this value, the better it does. All right, so let's take a look at the movie. Okay, so there's like some intro slide. Now you see, after about 20 training episodes, the agent learns to disentangle just 2 out of the 4 qubits. And I know that it's 2 because I see that 2 of the qubits fell below the entanglement threshold. Now, after 40 iterations, it can already disentangle all of them, right? However, it takes pretty long. It takes about 9 steps to do that. And the whole point now is to start minimizing the number of gates applied. And we want to minimize the number of gates because these gates are costly on noisy quantum computers. And today we only have noisy quantum computers. And so it first minimizes the number of gates, then it starts reducing the entanglement. Now you see that this curve always goes down to 0, which is pretty neat. And now in the end, you can basically follow what happens as you sweep through the entire trajectory. So you kind of see how it gradually builds these gates one at a time. And so again, I don't expect you to understand exactly what's going on here at this stage, but this is just to give you an overview of what this talk is going to be about. Okay, so in the following couple of minutes, I'm going to try to explain this graphs. Right, this comes up. Right. I'll give you a pretty compelling reason in a second. So that's the outline. So okay, why do you want to disentangle states rather than entangle them? That's the introduction and the motivation. I also am going to define what I mean by disentangling. I see a couple of students here, so maybe it's going to be nice for them to recap the most important definitions. And then, of course, we do this using reinforcement learning, and reinforcement learning is not anything that a physicist would know about, and therefore I'll also explain roughly how that works. And then I'll show you some of the results on 2-qubit states and maybe 5 or 6-qubit states. We'll probably won't have time to go within the applications in 40 minutes, but still, we can chat about them offline. All right, so let's go and see why do we want to mess up with entanglement in the first place. So as you probably know, quantum entanglement is essentially fundamental to quantum theory in the first place. What I mean by this is this long-lasting story that if you start from a Bell state, and if I trace out basically one of the 2 qubits, that is to say, if I measure the state of the one particle, then this is immediately going to collapse the state of the other one. And so this was first realized in 1935 by Einstein, Podolsky, and Rosen, and they basically called it spooky action at a distance because they didn't like it, they didn't like quantum theory, and they thought essentially it's incomplete. However, if you fast forward about 100 years, in 2024, we're at the verge of essentially making quantum technologies work, and the basic building block, or one of the basic building blocks for quantum technology, is exactly quantum entanglement. So how do we quantify entanglement? Let's say that we have an initial state like this psi. What I can do is I can trace out, say, the second qubit. I'm going to be left with the reduced density matrix rho 1 of the first qubit. And then I can compute the von Neumann entropy of this reduced density matrix. And if this number is greater than 0, then I know that my state is entangled. That is to say, there's entanglement between the 2 qubits. So this is a measure to quantify entanglement. Now, besides quantum technologies that I already mentioned, entanglement is also fundamental to quantum optics, where, for instance, you can entangle photons using beam splitters, or also to condensed matter physics, where we're interested in studying ground states of interacting systems, and in particular, a specific class of systems, the so-called spin liquids, have essentially long-range entangled ground states. And why do we want to study those? Because it turns out that they are both interesting, and typically we study them in quantum simulation because these kind of spin liquid ground states are going to help us build the reliable error correcting codes, whereas the beam splitters might one day lead to a quantum computer based on photons. I mean, these are currently under development. I wouldn't say that they are competitive, but at least one can think of doing this. All right. So I mentioned quantum simulation, and now with respect to entanglement, I want to just outline a couple of milestones. So the first one is that we can already implement perfect 2-qubit entanglers. So the entangling problem has been solved on the level of 2 qubits. This is actually done already around a couple of years or so. So that's not so difficult. What's more difficult is to realize states of many particles that all interact and they get entangled. And examples of such states are, for instance, the toric code ground state. This is an example of such a spin liquid, or the many-body GZ state. And I want to emphasize that the toric code ground state was realized on a trapped ion quantum computer. This is, I think, Honeywell's experiment a few years, well, 1 year ago. Whereas the GHZ state was realized in 2019 in the Looking group at Harvard. So it's possible to realize states which have multi-body and many-body entanglement. But now this is all very theoretical, very fundamental. I mean, sure, it's fun, but what are practical applications of, for instance, disentangling states? And Nikolai already asked this question. And here's basically the primary application of this. Let's say that I have a state psi from the initial. It turns out that this is precisely what, for instance, Kit was using in order to initialize states on a computer. So if you're using Qiskit and you want to prepare a certain state in the computer, what the algorithm behind it is going to do is going to take your state, it's going to disentangle it, and then it's going to take the same circuit and run it backwards, and so to prepare the state. So this is another reason why you may want to care about disentangling states. Of course, preparing certain states is one thing, but you can go one level higher. This is something that I won't be talking about, but in principle, people are doing this, which is circuit decomposition or circuit transpilation. That is to say, if you have a unitary operation that you want to implement on a quantum computer, how do you decompose this unitary operation in terms of elementary native gates, which your computer can process? And this is, for instance, an image taken from the IBM Qiskit documentation, where you have a certain unitary which is decomposed into these elementary gates. So this decomposition or disentangling, if you wish, of state is related to decomposing unitaries. It's related to preparing states. In the previous slide, it's related to interesting physical phenomena like condensed matter ground states or beam splitter dynamics and physics, etc. And also entanglement, control of entanglement overall is essential for quantum technology. So at this stage, I think I've given you enough reasons for why you should care about entanglement and the control of quantum entanglement. So now I want to so gonna click through. We first state Okay, so once again, we have a multi-qubit state psi, and the idea is to check whether it's entangled. And it is entangled if and only if this average single qubit entanglement is 0. And you can kind of see this straight away. So if it's a product state, if psi is a product state, then there's no entanglement whatsoever. Therefore, those guys are going to be 0 individually, and so is the sum. If you find that the sum is 0, then the entanglement entropy is a non-negative number, and therefore it means that all those summands have to be 0 individually, but if they're 0 individually, then psi is a product state. So that's how you see that. So this is now a measure that we can check how entangled the state is. Now what we want to do is we want to find a unitary U such that when we apply it on the state psi, we get the product state. However, we don't just want to have any unitary. What we want is a unitary which preserves locality. In other words, it's a unitary that is composed out of 2-qubit gates. And the reason why we want to deal with 2-qubit gates is because interactions in physics are typically two-body, right? So, all the gravitational interactions, Coulomb interactions are interactions between two particles. And so naturally, 2-qubit gates are much easier to implement in quantum devices rather than many-body gates. However,
Why is it called locality?
This is locality.
2-qubit gate is not a gate.
I would call it a local gate to distinct it from the 4-qubit and all the other gates.
So what is then the 0-qubit gate?
That's just the rotation. That's not even interesting, I would say. Yeah. So maybe what you wanna aim at is this bullet point here, which I want to emphasize. So I'm restricting myself to 2 qubits, but I do allow myself to place basically the 2 supporting qubits as far on the chain or on the register as I want. So I don't necessarily limit myself to adjacent qubits, right? I can also apply 2-qubit gates on distant qubits, and maybe this is what you say that it becomes less local. But it doesn't matter because it still contains only 2 particles. And these interactions can be implemented in a straightforward way, for instance, using trapped ions. There are Molnar-Sorensen gates or Siraj-Zoller gates, or using Rydberg platforms. There, I think the state-of-the-art is the Pichler gate. So you can do these things without a problem.
But then you the propel states are local, right?
How do you mean? I can take 2 qubits. Right, and I can do them, I can place them very far away, and this is going to be a Bell state on these 2 qubits. And I would call this local. Because it only has 2. These I wanna keep away from. And again, so my definition of locality has to do with how many particles have to interact in order to produce the gate at the same time, right? You can do 3-body gates out of consecutive applications of 2-qubit gates, and that's essentially what this is all about. So in other words, what I want is I want to take this unitary and I want to decompose it into a product of 2-qubit unitaries. And this is because that's what can be applied in the lab. I hope I will be able to get to the last slides where I will show you how actually you can apply this business on a quantum computer and that it works there as well. But any other questions about this?
Can you use other measures for entanglements? Why use entropy?
Because I like it. If you come up with your favorite entanglement monotone, you can put it in there. Yeah, that's not the problem. For pure states, they're all equivalent anyway.
This means that it doesn't work or mix into entanglement.
So once again, I have a pure state of L qubits.
So this means that it takes on for a pure state, not for a mixed state.
For a pure state of L qubits. And then any subsystem would be in a mixed state.
I understand that if your initial state is not pure, but mixed, then this measure is not 0 at T0.
That's right. And we're going to get to this point in the end. Then you can switch if you wish to entanglement deformation or something like that. And it works with all. No, I'll show you application on the device. Well, the real device will be mixed, but it doesn't matter. It still works. Right? That's what we want. Okay, good. Now, okay, if I run out of time, you're going to have to give me 5 more minutes to show you how it works, because otherwise it'll be unfair. All right, so once again, the goal is to find a circuit of 2-qubit gates, and this is an example of such a circuit, where you can take any initial state and you can basically map it to a product state. And for instance, you can parameterize these 2-qubit gates, and again, they don't have to be acting on adjacent qubits, but you can parameterize them by some parameters, variation parameters, or anything alpha. And so now the disentangling problem decomposes into a 2-fold optimization problem. The first one is the so-called discrete optimization. So find the optimal order of pairs of qubits to act on. And then the second one is the so-called continuous optimization, where you need to find the appropriate values of these angles, alpha, beta, gamma, delta, etc. So we have basically 2 problems to solve at the same time. And this is actually quite difficult because if you think about it for a second, the control space is pretty big. In particular, the Hilbert space itself is continuous, and it also grows, its dimension grows exponentially with the number of qubits. But also, if you fix the number of qubits L, and you fix also the number of unitaries that you can apply, the number of gates, then there are L choose 2 to the power n, so also exponentially many in n, different protocols.
Another question, to make it clear now, because we'll get off. Do you know the initial state?
It's any initial state.
Arbitrary initial state.
How?
Arbitrary initial state.
Arbitrary initial state. That's the whole point.
Which you don't have to measure it.
You will have to measure something about it. We'll come to that part. But it's not going to be a full state tomorrow. Because,
So
yeah.
Right.
Right.
You do not know the initial state, right? You start with arbitrary because.
So the whole point of using enforcement.
You do it without knowing the initial state.
So the unitary will depend on the state. Maybe you wait a couple of slides and then you'll see it. Okay? All right. But what I want to emphasize here is that there's a 2-fold optimization problem, a discrete and a continuous one. And you can go ahead and try to solve them at the same time, but of course it's it's not like the smartest thing to do. Instead, what we will do is we will focus on the continuous optimization problem, and I'll show you a partial solution to it, and then we'll actually use reinforcement learning for the discrete optimization. So let me tell you how to deal with the continuous optimization problem here. So the idea is the following. What you have is you have an L qubit state, psi, and then the question is how do you determine this U, which essentially reduces the entanglement. And what I mean by this is exactly the following. If I have an L qubit state, and I know that I'm only going to be acting on 2 qubits, then the only relevant part of the state for this operation is essentially the 2-qubit reduced density matrix. And from this 2-qubit reduced density matrix, the contribution to my cost function, if you wish, is going to be the sum of the two entanglement entropies that live on these 2 qubits. So this is before I apply any unitary. Now, the idea is, if I apply a unitary, then of course these entanglements are going to change. And what I want is I want to choose the gate U in such a way that the sum is minimal. In other words, if the sum is minimal, then because all the other entanglements entropies remain intact because the gate doesn't really change entanglement between them, then I'm also minimizing the average entanglement. So the question is now how to choose the U. What I want to show you now is just one way of doing it, and there are many, but just one that works, which we're going to do in the following way. So what we will do is we will diagonalize the 2-qubit reduced density matrix. And I'm going to basically do this with this operation U. And I will assume that the eigenvalues are ordered. Okay? This I can do. It's a 4x4 matrix, so it's not really that difficult to diagonalize it. Now, once I've obtained this object, then I want to compute the single qubit entanglement entropies. Therefore, I need to reduce it to a single qubit density matrix. And if I do this, you can probably see it right away. This is diagonal, therefore the resulting matrix is also going to be diagonal. And what I do is I'm just summing up the first two and the last two eigenvalues whenever I trace out qubit 2. But now my eigenvalues are ordered. And if they're ordered, it means that these two carry the most weight and these two carry the least weight in the distribution of the eigenvalues. In other words, the distribution with this ordering relation here, which I postulated, is maximally mixed. If you do that, you can show that such a gate U does the job. In other words, it keeps this value minimal. And so it therefore reduces the entanglement. Now, I want to make 2 comments. And one of them answers Nikolai's question. So the unitary depends explicitly on the state, but not on the full state, only on the 2-qubit reduced density matrix. And we're going to be making use of this fact. And second, this unitary is not unique. It's not unique because I can multiply it here from the left and from the right by any single qubit reduced, by any single qubit unitary. It just won't change entanglement between the 2 qubits. But we don't care. We only need one unitary to tackle the continuous optimization. And with this, there's also proof like in this paper, you can show that this thing keeps the entanglement minimal. So now we're left with the discrete optimization. And once again, the discrete optimization is the following. For each pair, we want to apply such a locally optimal 2-qubit gate in such a way as to disentangle the state. What we don't know is the order in which we're applying those. That's the difficult part. And it's actually much more difficult, as I showed you already, than solving the two-body problem. So that's okay, but I want to also impose extra features going in the direction of applicability. So what we want to do this with as few gates as possible, because this reduces the cost on noisy devices. And second, we want to disentangle arbitrary states. So a state, an initial state with no obvious entanglement structure. And that's the whole point of using machine learning for it. And we'll see in a second that we'll be able to recognize the structure of the entanglement and then give you the corresponding structure of the circuit accordingly. And one example of this an arbitrary state can be anything you want, but one specific example of such a state is the high random state or the family of high random states, where you just write down the state in terms of the computational basis and you draw the amplitudes from a normal distribution. So this is a difficult combinatorial problem, this discrete optimization. And so this is what we'll give to the reinforcement learning gate. But I want to argue why this is a difficult problem first. So let's say that I gave you this problem without any machine learning whatsoever, and then I ask you to solve it. Then what would you do? You would say, okay, let's just try something very, very stupid. So let's just do what I call a random agent. A random agent will select a pair of qubits uniformly at random from the L qubits that I have in the state. And then it's going to apply such an locally optimal disentangling gate. And let's do this. Just simply these 2 rules. And as we do this, we're going to be monitoring the average entanglement entropy as a function of the number of gates that we apply. So that's what I'm showing here on the right. On the x-axis, I have the number of gates, and on the y-axis, on a log scale, I have the average total single qubit entanglement entropy. And now what you see very clearly from this scaling is that the average entanglement goes down exponentially in the number of gates, which is actually pretty good. It means that the locally optimal gate that I showed you is able to get rid of the entanglement at an exponential speed. It could have been a power law, right? But it's not, it's exponential. But there's a catch. And the catch is that if you look at the time scale for this, so to measure the time scale, you can think of m as time, so there's a corresponding scale c. To measure it, you can think of the number of gates that are required in order to reach, let's say, a threshold of 10⁻³ and that's shown here in the inset as a function of the number of qubits. And what you see from that plot is that this time scale actually grows exponentially with the number of qubits. So even though I can go down exponentially fast in the number of gates, I actually have to pay an exponential, climb an exponential wall as I make my system bigger and bigger and bigger. And this is for high random states. And it has a good explanation, right? So let me try to explain, at least intuitively, where it comes from. So as I've already shown to you, what matters for these 2-qubit gates is essentially the 2-qubit reduced density matrices. I mean, the rest of the state is not so important. So let's take a look at one of those. Any 2-qubit reduced density matrix can be written in this form, where 1 is the 4x4 identity matrix, epsilon is some parameter, and then sigma is a vector of 16 Pauli strings, essentially, that we expand in the operator basis. Now, if I have a high random state, then you can show that that high random states have reduced density matrices that are exponentially close to the identity. And what this means now is that if I increase the system size and make it bigger and bigger, then I'm going to get exponentially close to the identity. But if I have the identity, any unitary that I apply to the identity won't change the state at all. This is where the mixins essentially enters. And therefore, you need longer and longer gates, more and more gates, until you can actually disentangle it. So this explains basically where the second exponential more or less comes from. But anyhow, this was a random agent, and it also shows, that the problem is inherently difficult. But let's try a different agent. So let's just try a greedy agent. A greedy agent would be the following, another very intuitive idea. So I'm going to say, let me try out all possible pairs of qubits. They're not so many; they're just L squared of them, roughly. And let's just apply for every pair of qubit the corresponding optimal 2-qubit gate. And then I'm basically going to end up with a bunch of possibilities. So I'm going to cherry pick that pair that minimizes the average entanglement. And that's the corresponding plot here on the left. And what it shows is that even though you gain a factor of 2, roughly, the number of gates, which is not bad, if you go from 700 to 300, it's actually pretty good. But the tricky point is that the exponentials persist. And so the exponentials are always going to be there. The exponentials are a property of only working with 2-qubit gates, if you wish, a property of what I call locality. And essentially, you cannot get rid of them. But what you can do is you can ask the question, is there anything better than a random agent and a greedy agent? Can we do something better using a smart agent? And in particular, what I want to do is I want to ask the question, can we do better using partial information about the state? Okay, so why would I think that you can do better by doing this? Let me just give you 2 examples. So, okay, can you do better than the random agent using information? Well, you'd better be able to, otherwise, the problem is not interesting. But the other question is, can you do better than the greedy agent? And here, I just want to motivate why, a smart agent could be better than a greedy agent to disentangle states by just looking at this picture. So whoever ever tried to unentangle a knot, you guys know that the order in which you pull these strings actually matters, right? And so this is really what we're going to be going after. We're going to be going after the order in which these gates are placed. And this is why we need a reinforcement learning agent that can basically plan ahead. And it's not enough to take a greedy gate at any time. I'll show you a comparison later on. But we cannot just use any information about the state. So what are constraints on the available information? One thing to note is that full state tomography is exponentially costly in the number of qubits, and therefore this is a no-go. As far as I'm aware, the world record of a full state tomography currently goes to Google, and they can determine the full state of a 6-qubit system. And that's basically as far as they can get. And this is really difficult. So it doesn't scale well. But on the other hand, if you only want to measure the 2-qubit reduced density matrices, then this scales only quadratically in L. So therefore, this is not prohibitively expensive. Now, in order to do this business, what I also need is 2 more things. So first, I need access to the average entanglement, because this is the quantity that I want to minimize. And then what I also need is I need to be able to produce those gates, because remember, I told you that the gates will depend on the state. Okay? And so the idea here is that if you measure all 2-qubit reduced density matrices, then it's very easy to determine the single qubit reduced density matrices from those, and therefore compute the cost function. But also from those, you can also, as I showed you, compute the optimal unitary. So by only measuring the 2-qubit reduced density matrix, which is our partial information, what we want is we want to do better than the random or the greedy agent here. And we're going to see basically what else we gain by using reinforcement learning for this problem in a second. All right, so that was the first part where essentially I tried to set up the stage and explain to you what the problem is. Now I see that time advances, so let me just move forward rather quickly. So those of you who never seen reinforcement learning before, reinforcement learning is essentially the way to teach your dog to sit. And the way you teach your dog to sit is the following. You say sit 50 times, and the dog maybe or maybe not decides to sit once. But when it does so, you give it a treat. So you reinforce a certain behavior. Okay, so that's the whole concept behind it. And reinforcement learning is essentially, in a nutshell, the mathematical formalism of doing this. But more importantly, reinforcement learning entails interactive dynamics. So it's all about the interaction between the dog and the human, right? And this is what we want to do. If you go back to the previous slide, we want to interact with the system, right? We want to measure locally what's going on, right? Without really destroying the state and see what comes out. Okay. So in reinforcement learning, what you have is you have an agent, this is the dog, that learns how to solve a task by interacting with its environment. And the way that this works is the agent is taking actions. The actions, for instance, to sit or not to sit. The actions are changing the environment, and then as a result, there is a reward, and the reward can be 1 or 0, or maybe a -1. But the agent also can observe the state of the environment. And so it is the reward and the observation that influence the future actions of the agent. So that's essentially roughly the idea. And importantly, there's a feedback loop. So this procedure repeats over and over and over again as much as necessary in order to solve the task. Now, reinforcement learning has been used for games. And one specific game that is relevant to our problem is the Tetris game. So it's actually possible to play Tetris with reinforcement learning. And the reason I'm mentioning the Tetris game is because if you have a certain type of entangled states, the so-called Clifford states, so states generated by a Clifford circuit, then it turns out that the entanglement minimization problem is exactly equivalent to the Tetris problem there. And you can actually read about it in this recent paper in Frank Polman's group, where they show that there's even a phase transition between an entangling and a disentangling agent in this system. Of course, in this case, you can reach much bigger system sizes. But the reason I'm showing this to you is because what's relevant here is really the question, right? So can we play these disentangling games in a smart way? So that's essentially the question that I want to get to here. So let me show you now how to turn this disentangling problem into a reinforcement learning problem. So I first need to define my environment. So the environment consists of the physical state or the quantum state with the qubits. And then from that state, I can determine the observations. The observations are going to be all 2-qubit reduced density matrices. Once again, a physical state is a mathematical construct. This is not measurable in the lab. 2-qubit reduced density matrices are measurable, also efficiently measurable in the lab, and therefore I'm going to be working with those. Of course, they don't contain full information about the system, and that's really where the interesting business is coming from. Then what the agent can do is, okay, it can measure these 2-qubit reduced density matrices, and then essentially the agent will be taking actions in order to apply unitaries on that gate. And the actions are the pairs of qubits on which to apply the gate. So I can either place a gate on qubits 1 and 2, or place a gate on qubits 1 and 3. And this can occur with different probability, right? So my agent essentially will be determining probabilistically which qubits to apply the gate on. That's the idea here. And what you see here in this histogram is essentially the probability that the agent has learned in order to apply those. And finally, what I need is I need to tell you about the reward. So what the whole business is supposed to do is it's supposed to minimize the average entanglement entropy. And as a reward, you can use actually many different functions. We've experimented with quite a few of those, and we can chat about them offline. But just to keep the discussion at a high level, it's essentially the relative entanglement change with respect to the previous step, minus the number of entangled qubits, which turns out to help. So that's overall the framework. So once again, just to recap, we start from the state. We build these observations, the 2-qubit reduced density matrices, and then we're going to process this inside the reinforcement learning agent. So you can think of this as a blue box. And out of the blue box comes the probability. And that probability tells me which pair of qubits to apply essentially the gate on. So of course, there will be a probability for any pair of qubits, but we're interested in of course, the one that maximizes, in the pair of qubits that maximizes this. And once I have the pair of qubits, then I have my machinery to analytically compute the optimal 2-qubit unitary to do that. So the interesting question here is, what about the agent, right? So, where does this come from, right? So if we zoom into the agent, then it will consist of two parts, a so-called actor and a so-called critic. This is for the experts. So let's first start with the critic. The critic is just a simple, fully connected neural network. So vanilla fully connected neural network. It's supposed to learn a property of these states, a specific property of these states. But the actor has, besides linear layers, it also has these orange layers. And I want to spend a little bit more time on the orange layers. So the orange layers are there. They're called transformer layers. And they're there to solve the following physically motivated problem. Let's say that I have 4 qubits as shown here. And let's say that my agent has determined that this circuit is going to disentangle the state of these 4 qubits. Now, it's very intuitive that if I swap qubits 1 and 2, then I should be able to readjust the circuit accordingly, and I'm going to get the same result, right? Because physically, it's still the same state. I'm just relabeling the qubits, right? So this essentially tells me that there is a symmetry, in this case, a permutation symmetry, and I want to build this symmetry into my agent. I want to make my agent aware of this symmetry. And to do that, it turns out that I need to so-called enforce permutation equivariance. And permutation equivariance, one way to enforce it is using transformer layers. Now, if you've heard about ChatGPT, ChatGPT stands for Generative Pre-trained Transformer. So it's the exact same architecture as from ChatGPT, except in ChatGPT, what they do is they explicitly break the permutation equivariance because ChatGPT is supposed to read words, and of course, the order in which the words come matters, right? Here, I want to basically restore it. And to restore it, I get rid of this embedding layer that they typically use. So we're going to be able to produce agents that don't care how you label your qubits in the state, and they can, once you change that, then they automatically realize how to adjust the corresponding sequence. All right, so now let me show you a couple of results. And I think I'm going to be running out of time, but you stop me whenever you think it's time. So let's just see what we get. So for 2 qubits, the problem is trivial. By definition, my local 2-qubit unitary basically disentangles the 2 qubits. So there's nothing to solve. For 3 qubits, it's actually quite interesting. It looks like with these locally optimal 2-qubit unitaries, I only need 2 of them, and I need to place them on qubits 1 and 2 and qubits 2 and 3. And if I do that, then I'm guaranteed to disentangle the state, to bring it into a product state after this procedure. Now let me explain where this comes from. So let's take with the 3-qubit state. This is an arbitrary 3-qubit state. I can decompose it using the Schmidt decomposition, and then lambda are my Schmidt values. But importantly, the rank of the Schmidt decomposition for a 3-qubit state can be at most 2. If the rank is 2, then it means that there are only 2 eigenvalues of this density matrix, of this reduced density matrix that are non-zero. This is essentially what this rank means, that there are 2 eigenvalues that are non-zero. But if there are only 2 that are non-zero, then these necessarily have to be the largest 2 ones because I've ordered them. And therefore, after I compute row 1, I have, if you wish, a delta function. And if I have a delta peak, then this means that at this stage, this qubit is disentangled from the rest, is factored out from the rest. And then you can basically do, the same thing. And you find that with only 2 unitaries, you get to disentangle any initial 3-qubit state. And this is, this is a rigorous result, right? You don't need any reinforcement learning for this. For 4 qubits, the situation is a little bit more challenging, and there is a similar argument, which I'm probably going to skip over. But let me just take a couple of 4-qubit states and see how our agent performs on them. So I take the agent, I trained it like I showed you in the movie, and now I'm testing it. So let's start from a state that I'm showing here. So I want to experiment now with the agent, see how well it does. So let me take a Bell pair, which is in a product state with another Bell pair. And the first Bell pair is on qubits 1 and 2, and the second Bell pair is on qubits 3 and 4. So I take this state, and the first thing that the agent does is it measures all 2-qubit reduced density matrices. I put these 2-qubit reduced density matrices in this blue box from the previous slide, and there comes out the probability of taking any, of placing the gate on any pair of qubits. And as you might guess here, because you know the structure of the state, the probability of placing a gate on qubits 1 and 2 is 50%, and so is the probability of placing the gate on 3 and 4 initially. But of course, you have to place a gate somewhere, and so the agent decides to pick the red one. So after it's placed it, then this Bell state will be factored out, it will be disentangled, and the system will be left with the second Bell state. And now the probability shifts almost perfectly to the second pair. So the agent now realizes that the entanglement structure is within the second pair, and therefore it decides to act on the second pair almost deterministically. And this is enough in order to disentangle that state. You're going to say, okay, well, I can do this without any RL agent. Why the heck I bother about it? So let's try something else. So let's try another state. In this case, I'm going to take qubit 1 to be in a product state with qubits 2, 3, and 4, whereas 2, 3, and 4 are going to be in a GHZ state. GHZ state is more interesting because it's an entangled state. So there is entanglement between all of these qubits, 2, 3, and 4. If you look at what the agent suggests after looking at the reduced density matrices, is it said you can apply any gates 2, 3, 4, 2, or 3, 4 with equal probability of 33%. And it doesn't matter which one you do. Therefore, we take 2 and 3. But once you do that, then according to this rule, I only need only one more unitary, and indeed the probability collapses on pair 3, 4. So two unitaries are enough also to disentangle that state. Okay, but you say, okay, again, GHZ state has a structure. I know how to create the GHZ state using a circuit, therefore I don't need this business here. So let's take a state where I don't know the structure of the thing. So what this R here stands for is a high random state of all 3 qubits, 1, 2, and 3. And if you see just a single subscript here, then it means that this is a high random state on a single qubit, and then these are in a product state among themselves. So this is now a state that I drew randomly. So you don't know where the entanglement lies in there. And this is actually the strength of using reinforcement learning for this business. Reinforcement learning now is going to tell me how to disentangle it. And the way it's going to do this, again, measure 2 qubit reduced density matrices, plug them in the blue box. The agent says, in this case, I'm going to apply a gate on qubits 1 and 3, and that's what it does. And then I'm going to apply a gate on qubits 1 and 2, and that's what it does. And this is enough in order to get to the target. So notice, it's effectively a 3 qubit state, and therefore, again, it only uses two unitaries. You can, of course, make it even more interesting. You can say, let me just take a completely random state supported on all 4 qubits. And this is completely crazy because there's no structure whatsoever. You just give it to the agent, and then at every step, it knows exactly where to place the optimal gate. And in exactly 5 unitaries, you can get to the target. It turns out that there's something universal about this structure. And you can show that any 4 qubit state can be completely disentangled using less than 5 2-qubit gates. But importantly, the gates are state dependent. And then there's something about the circuit topology that I don't want to go into. So this is a statement. You can actually prove this statement, but in the interest of time, let me just skip through. The proof is analogous to what I showed you with the Schmidt-Grams. You just count a couple of times this, and then you can basically show that you actually need 5 2-qubit gates, but if you turn it into C-nodes, no more than 10 C-node gates in order to do that. So it's actually quite efficient. For comparison, if you give this to Qiskit, Qiskit is going to take on average 21 C-node gates, so more than twice. All right. Okay, so now I wanted to show you something that Stefan prepared, which is pretty cool, which is, if I manage to get this to work. Let me see how this is going to go. So it's one of those things, but for some reason it doesn't show up here. What happens if I close this? Give me a sec. Okay, there we are. So what we want to do now is we want to really play with these agents. And Stefan prepared a nice notebook, which, by the way, will be available on the archive together with the paper. So that's what we care about. So what I can do here now is I can literally. I'm not presenting. No, yes, you might be. Oh, good that you told me. So now it should show up. Yeah. Good. So what I'm showing you here now is a Jupyter notebook, and this Jupyter notebook will allow you to play with these agents. So you can load the agent and you can basically test it, see how well it works. And what you can do in particular is you can apply single qubit rotations to it, or you can apply 2 qubit rotations, and you can specify which qubits you want to apply these rotations to. And what you can do is you can put in any arbitrary state, and we have a couple of states here that we've trained. So let me just give you this state, which is a W state on qubits 1, 2, and 3, and a high random state on qubit 4. W state is interesting because unlike the GHZ state, the W state has a 3-type entanglement in it. And therefore, it's slightly more complicated. But indeed, if you just step forward, actually, before you do so, the agent gives you roughly 33% probability on these pairs of qubits, and then you can step forward, and then the agent places the gate, the state changes, and now the agent looks again at it and says, okay, there's only one more step that's necessary to go through. Another thing that's pretty cool that you can see here is if you actually go and look at the GHZ state. So that's a GHZ state between qubits 1, 2, and 3, and then a high random state on qubit 4. And what you kind of see here is that the first thing that the agent will do is it will apply a gate on qubits 1 and 4. And this green bar here tells you how much this reduces the average entanglement entropy. So that's the delta entanglement average. You guys see that? Hope you do. And the reason I'm showing you this example is because in any other pair of qubits, you'll decrease the average entanglement entropy, except for this one. And yet the agent decided to take this one. So you kind of see here, these are the single qubit entanglement entropies. So they're all fully entangled, except for the last one, because the last one is, is in a product with all the others. So you see, like here, you're not gaining anything on the entanglement, and yet it decides to do that, because then it's going to be able to disentangle the state in just 3 steps. So it's actually possible to take suboptimal actions, right? And nevertheless, get away with a fewer number of gates and still do the job. So that's where having a smart agent really outcompetes having a greedy deterministic algorithm. Okay, I can give you the notebook afterwards, so you can play with those. I think I want to cut this short. So these were 4 qubits. We do have results on 5 qubits and 6 qubits. I want to go very quickly with that. So this is how it looks, by the way, if you want to disentangle 5 qubits. Again, the color, basically when it changes, you reduce the entanglement entropy by 1 order of magnitude. In the end, everything falls below a threshold. Interesting thing here is that there are actually some topological subsequences. So you can analyze this circuit. You can say this circuit doesn't mean anything because you start with a random state. So the state doesn't have any information in it. And yet, whenever you have no other information, the only robust thing left is topology. So you can have like topological classes of subsequences that allow you essentially to disentangle the state as quickly as possible. But what I really want to show you is a comparison between the reinforcement learning agent, the random agent, and the greedy agent to see how well they work. And to do the comparison, we're going to test them on states that are product states that look like that. So basically, where the product state is determined here. This is, I think, a little bit of an old plot I should update it. But it's determined by the subscript. So if you take this state, what it means is that the state R1 to 3 is in a product state with the state R4, 5, right? And therefore, this is effectively a 3-qubit state and a 2-qubit state. If you see that, then there's no product whatsoever. This is just a completely random 5-qubit state. And then on the y-axis, I'm showing you the number of gates or the length of the protocol here. And the 3 bars go between the random, the greedy, and the RL agent. And what you see, roughly speaking for 5 qubits, is that the RL agent is always finding shorter sequences. So it's always more efficient than the others. So this is for 5 qubits. Now you can say, okay, what about 4 qubits is the same? What about 6 qubits? It's also the same. But the cool thing is, the number here, the average or the minimum number, the average length of the sequence grows. So the same way that we saw this exponential growing when you increase the system size, this exponential is not resolved by using the agent, and it cannot be because it's a mathematical fact. But what you can do is you can go down, significantly. If you have like roughly 15 less gates, then you can do a hell of a lot more things on an actual device these days, just because you have less noise. Okay, I want to show one application of these things before we close this. So I should say we tested this also for reducing CNOTs. Maybe this is a nice application. So we tested this against Qiskit. So here you see the version of Qiskit. As I explained what Qiskit is doing when you want it to prepare a state is it takes a state, it first disentangles it, and then it runs the circuit in reverse order in such a way as to prepare the state. So what we ask ourselves is, how many CNOT gates does Qiskit use, and how many CNOT gates does our agent use? And this is essentially what you see here. So you see different colors. This Qiskit basically was using this version of Qiskit is using this algorithm by Shand et al. From 2006. And then different colors you can basically consider, Qiskit if you wish, with nearest neighbor gates only, or with all-to-all gates, or you can consider our agent with nearest neighbor gates and with all-to-all gates. And you see that in all the cases, the agent is essentially performing better. And you can also do this for 5 and for 6 qubits, and it also always performs better, except for the largest amount of states, which I can talk about afterwards. We know where this comes from essentially, but that works. If you want to apply this on a device, you need to check how resilient this is to noise. You can check it. So this goes back to Pesha's question about what if I start from an entangled state? And what you can see is that, of course, in this case, you don't bring the entanglement exactly to 0, because there's still, because the entanglement entropy will measure some sort of entanglement with the environment. But nevertheless, this agent will consistently decrease the average entanglement entropy, and therefore will, for as long as the noise is sufficiently small, right? So there's some threshold. For as long as the noise is sufficiently small, an agent that is trained on a noise-free environment will actually produce good circuits. And this is for Nikolai, the last one. So we decided to test it on real NIS devices. So we got like compute time on INQ's devices that allow us to place like distant gates. We also got compute time on IBMs and decided to try and see what comes there. And this is essentially one of these results. So remember those states, the bell-bell pair, this time between qubits 3 and 2 and 1 and 4, it doesn't matter. What we can do now is we can try and we can use the device, we can measure the reduced density matrices on the device, including all the noise that's present there, right? So including all the noise, and then using these noisy reduced density matrices, we check what the agent suggests us to do. And that's what the agent suggests us to do, right? And you can kind of see in the first step, it roughly recognizes that it's 50-50 between 1 and 4 and 2 and 3, which is what it should do, because these are the two bell pairs and there's nothing else. And then it chooses, 1 and 4 for whatever reason. If it chooses 1 and 4, however, you would expect this probability to collapse completely, 100% to the remaining bell pair, but it doesn't, right? They're still almost equally likely, and how likely they are basically is determined by how noisy your device is. And you can kind of see here, in this graph, the average entanglement has a number of steps. In this case, there are only 2 steps, and these are the values. The state vector simulation, which is the Qiskit simulation, gives us almost perfect entanglement, so almost 0. Not exactly 0 because there's noise, but of course the noise model in Qiskit is not the real noise model. The real noise model is much worse, and therefore we have the red curve. So this is basically how low the von Neumann entanglement goes. And now this is for Pesha's question, right? So in this case, however, you have reduced density, so you have mixed states, and when you have mixed states, entanglement is not measured by the von Neumann entropy. Entanglement is measured by another quantity, which is called entanglement deformation. And for these states, we actually can compute on the device the entanglement deformation. And what you see is that if you actually look at the entanglement deformation, then the quantum device actually goes down to 0. And this is what the agent really does. So we train the agent to minimize the entanglement. The agent does minimize the entanglement, right? If you have mixed states and you measure the von Neumann entropy, you're just measuring, the wrong quantity. So this was for the bell-bell state. You can do a bell-bell state that think on different pairs to see that the agent is permutation equivariant. In other words, it doesn't matter. And then what you can also do is you can try it on more interesting states like the GHZ state, and for the GHZ state it also works. Of course, the entanglement deformation here is a little bit more tricky because the GHZ state is only bipartite entangled. I'm not sure whether Rick had tried this on a W state, but the W state will probably have monotonic decreasing curve. What's important is this value here at the end, right? In the entanglement deformation. So this always goes down. All right, and so I want to leave you with this movie again. Now we're going to watch it one more time and hopefully you'll understand it a little bit better. So this is now the training process for the agent. This is the training curve. After 20 iterations, it can disentangle 2 qubits from the system. If you train it for longer, after 50 iterations, it can basically take all the entanglement out, but the circuit is too long. And now what we're going to do is we're going to start, or the agent will start to learn how to reduce the number of gates. And we want to reduce the number of gates because we want to deal with noisy devices. And what we also want to do is we want to minimize the average entanglement time. And this happens after about like, I don't know, 1,000 iterations. So I think the agents that I was showing you today, they were trained within maybe 2,000 iterations or maybe 5,000 iterations. But of course, how long you need to train for depends on the number of qubits that you have in your system. Like there's this exponential barrier that you won't be able to go. All right. So with this, I'd like to thank you for your attention. If you have any questions, I'd be happy to answer them.